Hi everybody, this is Tom Cherryarms with the FujiNet project. As some of you know, I'm working on a version of FujiNet for the Atom, and this includes the configuration programs that the Atom needs to run in order to configure FujiNet. These are written in C, so I thought I would take and show a little bit of what was possible and what you gain by writing programs in the C language for the Coleco Atom. To do this, I've basically set up a workspace that on the left-hand side contains a shell window, which I will be using to issue commands to the compiler as well as running the editor, etc. And on the right-hand side, we have a copy of Colem acting as an emulator to show the finished results. I do also have a Coleco Atom running on a video source. It's currently hidden so that we can see some bits and pieces in CPM in just a moment. But first and foremost, how do we write these programs in C and get them into a form that is usable on our Atom? Well, in my case, I'm using the excellent Z88DK software development toolkit. If you go to z88dk.org, you'll see this website right here, which gives you a nice overview of the entire toolkit, which includes a compiler, an assembler, a whole bunch of associated utilities, including application packaging utilities and utilities for making shared libraries, and a comprehensive shared library for all of these various functions that you would use in C, mostly written in assembler, so it's nice, tight, and compact, for over 100 different targets. And as you can see right here, it's very easy to use, even if all you're doing is compiling a single C program, specifying targets. And when you specify targets, it will automatically take and call appmake, which will take and package up your binary in a form that you can immediately use with your emulator or disk emulator device. In the case of the Coleco Atom, we support not only CPM format disk images, but we also support, it also supports digital data pack formats for EOS binaries as well. Not only that, but you also get a choice of 2 different compilers. By default, the excellent small c Z80 compiler is used, SCCZ80. But if you want to use SDCC, you can. You just specify it when you call the ZCC front end. We'll go ahead and put this out of the way for a moment. And we will set up our workspace here. Go into my workspace window, and we will go. I've unpacked my Z88DK distribution into a folder called Z88DK under my workspace. And if we go into it, we see a whole bunch of associated files here. You see, for example, the binaries are in the bin directory, and you see, if you look close enough, you see a handful of shell scripts for doing things like setting up your environment for both Unix and for Windows. And you also see VS Build hooks so that you can use VS Code. And not only that, but there are Docker files for running Z88DK build pipelines inside of Docker containers for automated builds. And there's even an Azure pipeline declaration so that you can take and run compiles inside of Azure pipelines. And all in all, very, very nicely put together. We can see some of the bits and pieces of the binaries inside of the bin directory. We have the ZCC front end, which is what you use. It typically calls most of these other utilities. But you also have the Z80 assembler if you want to use that directly. You have appmake, which does all of the work of taking your binary and putting it into a usable distributable form. You have things like a disassembler here, a librarian for building shared libraries and copying them into place. You also have an NM utility for looking at symbol tables and so on. All in all, everything that you would need for C or assembler development kind of ready to go, ready to be used. Excellent. So With that, we'll go ahead and get out of here since we're already set up. And since all I have to do at this point to make it work is to use the set environment shell script to set up my environment variables. And at this point, I can call ZCC from anywhere to call the compiler. So let's start with building a simple little hello world program. I'll go ahead and go into Atom Hello. And for this, I have a make file that I just take and carry around with me. If you want, you can get it from me. It's easy enough. You can pull it from GitHub and adapt it for your use. And it sets up a whole bunch of nice little things so that all you have to do is put your source files inside of source, and it will take care of building and dependencies, everything as you need. You just set your C flags and everything else as you need them. C flags are the parameters that get passed to the C compiler for for the individual source files. And in our case, that is as simple as specifying plus calico and subtype of atom. LD flags are for the linker to take all the individual object files that are produced as the result of the compilation and to bring them all together with everything needed to resolve all of the symbols inside those object files and any libraries that you need for any library functions that you may call. We have a similar situation here where we set the machine type and subtype, but we also have right here some additional things like setting up the font that we want to use by default, the name of the target executable. We want to create an application when we're done, so we have create app. But I also have a library here that I've written called Smart Keys for making Smart Keys type applications, and so that is linked in as well. The nice thing about libraries is if you're not using, it only links in the functions that you're actually using, so it's efficient on that route. We also have AS flags for passing in specific assembler flags as well. Nothing special here, just setting the machine type and subtype. And the rest of the makefile basically just deals with anytime we encounter a C file, run it through the C compiler. Anytime we encounter an assembler file, run it through the assembler. And finally, when we're ready to take and build everything together, we link it all together with the objects and the LD flags that we have here and do the right thing. We have some simple maintenance commands right here, basically just to do cleanup as well. So we can clean out the binaries and everything when we're ready to, for example, commit it into GitHub. So with that, we can go in and go into the source folder, and we can see in the source folder we have the assembler and font binaries for the system font that we want to use. This is specified up here in the pragma redirect so that the standard library will take and use them. And we have our program code. And we'll use Emacs as my main editor here to edit this. Now, we have up here two header files which include function definitions, so that the compiler will take and know the format of these functions, the parameters that they take, and any data structures that they may actually need to use. Quite nice, I think. In our case here for Hello World, I'm using the cross-platform TMS 9918 functions that are in msx.h, as well as a simple console IO input and output routine called conio. We then have to, at the very least, define a main function here. Since we're not doing any command line arguments or parameters, we just do void here. We set up the graphics mode, we set the color, and then we take and print the result for the string that we want to print. Easy enough. And to build it, all we really have to do is call make. I'm going to use the compile function that's inside of Emacs here, hitting Alt-X and compile. And since we're in the source directory, we actually need to go back to back1 directory and run the make here. Now, looks like we have one issue here that I need to fix. No big deal. Wrong function name, which we can get the function names if we actually take and go into Z88DK include msx.h. And yes, this is all, I'm doing this all entirely off the cuff here. And you'll see that there are a couple of different invocations that you can use. In this case, I'm using msx set mode here, especially since it's a fast call function. msx set mode, set the function appropriately, save the file, compile again, and you'll see right here it's created. When we actually take a look at see what's created, we go back into the hello folder here, we'll see that we've created a digital data pack right here. And as part of the process, AppMake has actually taken and created a bootstrap loader for us, which it takes and puts into the DDP as sector 0. But we also have our binary here, so you can see how big your binary is in total. So now all we really have to do is just run the program. And we can do that. I'll go ahead and go into the emulator here, file open, and I will go into that folder. Atom hello, select atom hello here, open that up, and we can see our little application coming up as intended. That's all we really had to do to take and display something on the screen here. All very nice, all very well. You can as well, if you really want to, use things like the VRAM directly if you wish. You can do things like that by basically doing, let's go ahead and bring ourselves back into a single pane here. Let's do some changes. We'll go ahead and set up for graphics mode 1 just to take and pull this across. And then we'll start building a program that basically writes directly into video RAM. Again, we'll use the Z88DK include msx.h. And I apologize here, I'm literally improvising this as I do this. And I will use the vfill function here for VRAM fill. And we'll start by looking at the appropriate VRAM addresses and putting in, just for example, we'll go ahead and use 2000, which is where the video RAM is currently set. We can actually take a look at this. If we go to Z88DK and lib source and lib target Coleco def EOS def, and we can see where our default name tables, default color tables, and everything will wind up being. So we'll put that in 2000, and since we're using graphics mode 1, we're really only using 32 color entries here, and we'll just kind of do a little bit of randomness here. And we want to take and make sure that this is locked off to a single byte. Cool. Okay. Groovy. And we'll take and just lop this right into a little endless loop here. Open it up. Let's have a look. And reset. Oop. Not quite what I was intending, but we shall try anyway. Here, give me just a moment. Sorry about that, fellas. There will be a couple of these moments in the video where I have to improvise a little bit. But went back through, realized what I was doing wrong. Basically, I was using the wrong parameter counts here. So basically, for MSX vfill, if we actually take a look at the parameter invocation here, we have an address, which is an address in VDP. We have the value that we want to write into there, and we have the number, the length, the count, how many of those we want to write into that RAM. So if we take that and we apply that to 1800, which is the pattern table, name table here, we can basically fill the screen with the same character very quickly. And so if we do that, we compile the result. We're filling an entire screen, 768 bytes for every character on the screen. And this is what we get. As you can see, yeah, works out pretty well. We can take that now and modify that to instead, let's modify the color RAM. And actually, let's add that on top of it. Sure, why not? Boom, 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 boom. Wow. Just do that. Wow. Let me use the method I want to use here. Sure. And we'll do this again. And since we're in graphics mode 1, we can just change for the 32 color entries that are currently here. So let's go ahead and just do that. Boom, boom. Compile, bam, bam. And I will reload and reset. And yeah, it's actually happening fast enough. There we go. Whee! Now, we could change that. You can kind of see what's going on here. If we take and pause it, boom, you can see that it's altering the color table. Boom, 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 boom. So let's go ahead, modify that for mode 2. And do a few adjustments here. The name table entries are just the same. Since we're in mode 2, though, the number of entries vastly increases. So this will be a bit longer. So let me go ahead. I have to hit reset. And you can see that now this takes a bit longer, but we are indeed altering every single entry in the color table at the same time that we're also writing to font table here. Now, since we're in bitmap mode, though, it doesn't have quite the same effect here, but that's okay. You kind of get the idea. You can write, you can read, you can write to the hardware directly to do whatever the hell you want. And it works out rather well. Conversely, anything that you write, by taking and modifying, we had the hello world in here. We put that back just to kind of show you. Set MSX color just so that we have something, because the OS doesn't really set much of anything up by default. Let's see, 177 here, whatever, and then we just if we take that and modify the makefile, we can modify the makefile so that instead of having a machine type of Calico, we can have a machine type of CPM. Subtype's the same, but the difference is here, what's actually going to happen is instead of creating a digital data pack that boots, we're going to create a CPM com file, and AppMake is actually going to take and bundle that into a disk image for us. So if I take this now, and build the result, now if we do XD again and have a look, we'll see that our hello world is here because we haven't cleaned that up. But we have an Atom hello, a CPM version of the software, and a disk image that's ready to go. Now, if we take and actually go ahead and bring up my capture device here, and we were to mount this, AppMake would create a disk image with our Hello World program. And build us our Hello World program automatically here. Now, since I didn't do any graphics calls or anything else, it just output this using the console routines. But if I use MSX set mode, etc., it will take and set up the screen appropriately, and you'll be able to use VDP functions to directly write to video memory, whatever, doesn't matter. The only restriction, of course, is the same for any other CPM programs that use the VDP interrupt, basically because the VDP interrupt is hard-coded, and it just happens to be in the middle of CPM's temporary area. We really can't use VDP interrupts in CPM. But other than that, you could essentially take the same program that you were writing in for EOS and target it for CPM, basically just by changing the output of your makefile. There you go. I'm going to end this video here for the third part of this video to talk about some of the other libraries and things that I've been working on. One of those is a library called Eos Lib. And Eos Lib is essentially a library containing all of the various EOS functions that are currently in the EOS 5 ROM, and providing bindings for them. And in fact, if we actually take a look at one of them, for example, let's take a look at something simple like the exit to Smart Writer. And it's essentially just a call to the appropriate routine. For more complex bits and pieces, such as EOS write VRAM, we take and marshal off the appropriate parameters, number, address, buff, just as you saw in the other routine, putting them into the appropriate registers, and then calling off the appropriate routine. Much the same thing. But because you can do that, you can essentially take and write little test programs, such as this program, which just uses the console routines to do some output. And since I'm only using the EOS routines here, I take and do any setup that I need to do, such as setting the appropriate graphics modes, setting up the border color that I want, putting the appropriate addresses into the VRAM table so that EOS knows about them, loading ASCII into the VDP, and then filling the color RAM with the background color that I want, followed by an EOS console init, and then doing some EOS console output. The result looks like this. if I go ahead and go into Workspace, go back into Eos Lib here, go into Tests, Console Output, run the Scratchpad, and then reset the hardware, you can see here that we have access to the Atoms EOS routines, and you can see the cursor just kind of flipping around here. This is in graphics mode 1 here, and you can see the output's pretty fast. It works really well. So you have access to all the EOS functions as well, in addition to cross-platform functions. Oops, I just realized I still have this open, so do that. There we go. Again, improvised. And you can see that it's working quite well. Yes, folks, I am doing this on the fly. But this is just an example of using the EOS routines here to take and use the Atom directly rather than using the cross-platform routines. We have the ability to do that here. Can this be optimized? Absolutely. Every single one of these bindings can be done in assembler and called effectively. We can take and crunch this down by at least a third, if not a half. No big deal. So we'll go ahead and exit. I don't want to save anything. I didn't really change anything. And if we go, I will take and pause this for a moment. And if we now go into Smart Key Libs, this is the other library that I wrote here to take and handle basically drawing applications that look like smart applications, the applications that Coleco and Laser wrote. So for those, again, much the same structure. We have the source for a number of functions which do things like set up the appropriate graphics modes, set up the appropriate display, display the smart keys on screen, clear out the smart key area, display the caps, set up the attributes, create status messages, and etc. In addition, we also have the example code. We have several examples that can be run here, and we can take and look at each one of them. I'll take and build that one. We'll take and build this one. And we'll go ahead and build select images here just to see this one, because this one actually has the full set of proportional font keys and everything else. And in fact, I'll just show that one because I haven't converted the other two over to the new format now that I think about it. So with that, all we have to do at this point, go ahead, go into Smart Keys Lib, examples, select images, and reset. And you can see right here, we have a nice little proportional font output here. None of this is optimized yet, but you can see that I'm controlling the screen quite nicely, producing an output that looks absolutely great. The smart keys look like smart keys, and the text is nice and proportional so we can get more characters on screen while maintaining maximum readability for each character. If we take a look and see what's inside this code here, for example, we'll dig into the examples so that we can take a look at it. And you'll see this is basically just a display example. We have our cross-platform graphics UI here. We have standard lib because I have some functions that need it. We have con.io for the console output here, although I'm not really using it here. That could actually be removed. Graphics for graphics output, and finally our smart keys library, which I've put inside of Z88DK's include directory. Smart keys set mode essentially takes and sets up the graphics mode, sets up the color RAM and everything to give that nice cyan background, and gets everything ready so that that looks great. Then we can immediately start to go ahead and do things like, the welcome to FujiNet bits. And for this, basically, I'm just setting up color attributes to do things like, let's set up the blue bars here using V-fill to take and fill the majority of the screen here with the white and little bars on the top and the bottom. And then I do an extra one here for left side blue. I could actually replace this with a vertical fill function that would be even faster. But I did this here just as a loop iteration so you could see it basically creates these bits on the left-hand side. You see this? Now there was a sleep here. I could put that back. And if we actually put that back, compile that. Take that, compile that, reload, and we'll see the status display actually come up this time. Hardware reset. Oops, sorry. I have to reload the program. And we can see the status display here. And this is actually one of the interesting things about the Smart Key library. You'll see here that some of these actually have null values here. Anything that has a null value gets, that particular keycap will be drawn as yellow. This is ostensibly so that you can have room for the status display, which writes in the black on yellow text that's customarily used for the status bar. And for anything that you want a keycap to go into, it will automatically take and draw the keycaps, set the appropriate text, and see, since I have a null here, there's a yellow in the middle. And then you can also set the text color appropriately here using MSX Color and use the Smart Key Put S here to take and draw the Smart Key's text directly on the screen because that function is directly exposed. Now I could, for example, just do a quick V-fill here, recompile that, and we could see the result for a selection bar. And there we go, boom. And so on. So you can see, very easy to get visual stuff done quickly. Now digging into this a little bit, we'll dig into this a little bit here. If we actually take and go into Smart Keys Lib and go into source, you can see some of the individual functions and how they're put together. Smart Keys Set Mode is just a little wrapper around these functions here to take and set up the video mode. Smart Keys Clear is just a quick little wrapper that clears out the bottom Smart Keys area using MSX V-fill. Smart Keys Adder is probably the most complex of the bunch, and essentially what it does is because I'm using bitmap mode 2, and each color entry is a single 1 pixel by 8 pixel by 1 line of a character cell. There are 8 of them for a single character cell. So I need 8 of those for a single character cell here, and we have those for the different color values for odd smart keys, normal, and those with a keycap, even entries, those with a keycap, and attribute entries for the yellow. And because I've defined these, I can simply take, and when I create the attributes, I can set them up in terms of the character cells that I want to go there and have them automatically set up automatically. And all I'm essentially doing here is checking if these are false for whatever reason. For example, they're set to null, then we take and turn them yellow. using memset. And then once it's all done, we take the resulting buffer that we've created here and write it all out to the VDP all at once. Smart keys put S is the text output routine. And the font definitions for this come straight from the Smart Writer ROM. And the format of these particular entries, there are 9 bytes in each entry. The first byte is the number of columns, the number of pixels, the length, the width in pixels of each character, typically up to 8, although it could be more. You can see right here, for example, space, the pound sign here, and for each one of those, the bitmap value. And all of these are in ASCII order, so it makes it very easy to use. And the thing that I added, the Smart Key ROM does not have any of the lowercase values, nor the rest of the ASCII character set. So what I've been doing over the last day is essentially taking and drawing all of the characters that you see on the right-hand side that are lowercase and building a font that matches the Smart Key bits inside. So once that's done, essentially we're writing a string to VRAM, and the following routine that you're going to see, the Smart Keys put S routine that you see in my example, or do I have it open? No, I do not. Okay, so let's open it. Oh, come on. Select images, UI, source. Smart Keys put S, of course, 2 values, an X and a Y pixel value, so you can put this at any pixel on the screen, and the text that we want to output, up to 1 line's worth. So the first thing we do is we make sure that we map this to an appropriate, we take and loop through each individual character until we see a null. If it's a new line, then we take and emulate a carriage return with a line feed. Otherwise, it maps directly to an ASCII character. We multiply it by 9 to get the appropriate entry into the table. Can this be optimized? Absolutely. We can basically put these values in a separate table, for example. And of course, write all this in assembler. This is all, first thing is just to get it working, then you make it faster. We get the appropriate font entry based on the offset that we've now calculated. And then for each pixel that is set, we take and set that pixel on the bitmap. Yes, we are plotting 1 dot at a time. And again, this can be made faster, but I wanted this to just work first, and then we can make it faster. Once that's done, we take and we move the X position by however many bytes, by however many pixels we found with the width, advance to the next character, and repeat. So that's essentially all of those routines in a nutshell. And I'm going to go ahead and end the video here, but I wanted to kind of show you guys kind of where I am at the moment. My goal right here is basically to just take and write a set of C routines that can be used to make nice looking and consistent applications on the Atom, and for myself to use these to create the FujiNet utilities that will be used on the Atom to control the FujiNet. So with that, I'm going to take and end the video here. I hope you guys have enjoyed it. I hope it was informative. If there are any questions, feel free to ask me. You can find me, of course, on Facebook, on Twitter. On Twitter as TSCHAK909. On Facebook as Thomas Cherryholmes in the Coleco Atom group. TSCHAK909 in Atari Age, for example. Other places as well. And, okay, so I've been talking for a while now. I need to stop. Ugh. Get a drink of water. So until next time, guys. Have fun.